Week 11, Part 5. Now I'd like to round out your whole picture of light and electromagnetic radiation to include another very different effect that's often a little bit hard to understand, although it's basically very simple in one sense. But let's start with some history again. Going way back, light, visible light, was always viewed as particles streaming, following straight paths and such. It was in 1801 when Thomas Young clearly demonstrated the wave nature of light. Uh, that was by his double slit experiment that I will actually, I think, show you at the very end of the course. But in this understanding, the different colors of light are simply different wavelengths of light. And so they're related by the speed of light being f times lambda. So different colors are different wavelengths of light. And there's a whole lot of physics that can be explained very, very well by thinking of light as simply a wave. But in 1905, Einstein explained what was a very puzzling experiment at this time, the photoelectric effect. When you shine ultraviolet light on metals, uh, the metals, electrons get ejected from the metal. And measuring this very, very carefully and looking at it and seeing how it behaved when you turned the light on in various ways and tried different colors of light and such, it just made no sense with the wave theory of light. It didn't act like a continuous thing. It acted somehow like the light was coming in discrete chunks. And so it was Einstein who explained it all by assuming that light, in fact, was discrete or quantum or particle, um, that there were particles of light, we call them photons, that they came in certain sizes, and that each individual photon carried a little bit of energy, and that was enough energy in some cases to kick an electron out of the metal. And so the minute you had some photons, they could kick electrons out. The amount of energy in each photon is, however, extremely small. This is the formula that tells you the energy of the individual photons. It's h times the frequency, or if you want, you can write it as h times c over lambda, where lambda is the wavelength. So the energy of the individual photons depends on what wavelength or what color they are, with blue light having higher energy and red light having lower energy, the individual photons, that is. But these amounts are extremely small because this constant, h, that's Planck's constant, is such a very small number, 10 to the minus 34. So the light is discrete. It comes in these little pieces, but the pieces are very, very small. And for many different kinds of experiments, you don't notice the discreteness at all. You just see light as being very continuous and very wave-like. But we generally understand emission and absorption of light as occurring in these discrete pieces. So for instance, here's a funny little model of an atom. An electron jumps from an outer level to a lower level, drops from a higher level to a lower level, and in the process, it emits a photon. An individual photon of light is emitted by that, going in one particular direction. Let's use this formula up here and calculate what is the energy of a photon. For example, what's the energy of a photon of visible light? Visible light is 400 to 700 nanometers. Let's just pick 600 for somewhere in the middle there. And if you use that formula to calculate hc over lambda, here's h, this very small number, that's the speed of light. And here is the wavelength, lambda, 600 nanometers, 10 to the minus 9 meters. And you get 3 times 10 to the minus 19 joules. That's an extremely small amount of energy. But then if you remember, a while ago we were talking about energy for electrons and came up with a completely different unit for energy, the electron volt. And do you remember the way of converting between joules and electron volts? It's just by multiplying or dividing by the charge of the electron. So if you take that 3.3 times 10 to the minus 19 joules and divide by the charge on the electron, you find out that the photon, a 600 nanometer photon, has an energy of 2.1 electron volts. So in fact, that's the kind of photon you would get if an electron jumped between two energy levels that were 2.1 volts apart. It's hard to put these two ideas together in our heads. We think in terms of macroscopic things in which things don't behave this way very much. But it really is true. And physicists get away with not really needing to put these two together much of the time. Quantum mechanics does that, but quantum mechanics is hard. And so what we do in general is to just look at what kind of process is happening. And if you're talking about the creation or the absorption of light, when you're creating photons, creating light or absorbing light, then that happens in a particle-like way, and you're creating photons or you are absorbing photons. But the propagation of light, as it goes from one place to another, it scatters off different things, or maybe where different parts interfere with each other, that all happens according to wave-like behavior. Now I'd like to take a look at the entire spectrum of the electromagnetic phenomena. It's a wonderful chart here in a book by Hecht. This is the book, better. Making sure so the backside doesn't show through. This is an optics book by Hecht in which he lays out all of the different types of light. So there's visible light right here in the middle, and then these are log scales. Way over on the left is frequency. If you start way down at the bottom, you've got radio waves of one kind or another with their frequencies in megahertz, or move on up and maybe you get to gigahertz for even higher frequency radio. And then as you go up still higher, you get into microwaves. And as you're going up in frequency, notice that the wavelength is getting shorter now. Frequency is increasing, wavelength is decreasing. And so microwaves, which are so named because they have wavelengths that are micro in some sense, that are short. They aren't actually, well, yeah, they aren't in the range of a micrometer, so I'm not quite sure why that name came about. But you can see as you get to higher and higher frequencies, shorter and shorter wavelengths, then we call it microwaves. And if you go still further, you get into the region that would be called infrared light. Notice as we're going along this, that you can also calculate what is the energy of the individual photons. And Hecht doesn't even bother with it down here. The numbers are so tiny, even in electron volts, it gets to be small. So you just don't notice it at all. You don't notice the discrete nature of this kind of wave. Radio waves, yeah, in principle, they have photons, but we don't notice them in any real way. So here as we're approaching visible light, you start to notice the discrete nature of it, and the individual photons have energies of around 1 eV as you get into visible light. The wavelength is around 1 micron. The frequency starts to be numbers that don't make aren't very useful again. When you get up to really light and ultraviolet light and X-rays and gamma rays, we don't talk about the frequencies anymore. You still talk about the wavelengths, and those get shorter and shorter and shorter. Ultraviolet light has shorter wavelengths, X-rays still shorter, and you go up to even shorter wavelengths, we call them gamma rays. And here the photon energies start to be stupendous. 1 mega-electron volt. That's a lot of energy in a single photon. It can do a lot of damage. Over on this side of the chart is very useful. It tells you where you get these different kinds of light and what are some of the sources that you might get. So visible light comes from motions of the outer electrons in atoms. Infrared light comes from molecular vibrations and rotations. Then the inner electrons start being responsible for ultraviolet or even X-rays. Or, yeah, I guess there's sort of a mixture between these. But the electrons, when they jump between different levels, if they're inner electrons, you're creating X-rays. If they're outer electrons, you're probably creating ultraviolet light or even visible light. And then gamma rays come from changes in the nucleus. When the nucleus changes from one energy level to another, that would involve the emission or absorption of gamma rays. And different ways of detecting these types of light and ways of artificially creating those different kinds of light. It's a wonderful chart. It's got a lot of very useful information in it.